If you remember your school physics days, you've probably seen this arrangement. This has a gas discharge tube with a noble gas in this case neon, eliminating a slit here in this collimated part of a spectroscope. Quite often they would use a prism, or in this case a diffraction grating, and by moving the telescope eyepiece at this side you can spot the actual interference pattern produced by this lamp. And that's roughly as far as it goes. It'll go into describing what the light is emitted from electron transitions in the gas, etc. But that's about it. I wanted to go a bit further and look at something slightly different. And I also can't really use this setup because I can't get a camera to take the image. So I have to redesign this arrangement as well. So this is another little light you might come across in spectroscopy in school. This one is the discharge light for sodium. Sodium is an interesting thing. One is that it's right in the very sensitive part of our vision, so they were used a lot in street lighting until recently. But they also produce two very close lines together, known as the sodium D lines. This being the year of quantum science, I thought it's maybe worth having a little bit of a delve into how these lamps produce their spectrum. This is the setup I'm going to use. I've got my light source here, and I have a spectroscope built out of a piece of drain pipe actually. It's a very narrow slit at this end, and that's allowing a kind of spot of light onto a diffraction grating which sits here, and it's using one of these reflective style diffraction gratings, and that then produces an interference or a diffracted pattern in this part of the tube where I have a small digital camera which fortunately focuses onto the beam from the diffraction grating, and I can take an image of it. So the interesting thing is the double line arises from a single electron transition in the sodium atom, but the split is the result of the electron spin orbit coupling. So we'll start up the lamp and take a bit of a look at what that means. And of course sodium is a metal at room temperature, and we have to wait till it heats up. So this is the lamp fully heated up, and if we look at the spectrum for this lamp we can see this, it looks like a single line, but it's actually got two very close lines there in the yellow. If we zoom in you can just begin to see the difference. There's actually a gap in the middle. This is what we really want to see. Oh, well done for following so far. This is where I think it gets a little bit more interesting. This is the high pressure version of the sodium lamp. This is a high pressure sodium lamp. It produces slightly whiter light. And we're going to look at the spectrum from this lamp as it heats up and see what happens to the spectral lines. So set up as before, still our spectroscope, and we now have the high pressure lamp in place. So as before, we'll have to wait till this heats up, but the current in these is very high, so the heating up process is quick, and I've also tried to speed it up. So initially you'll see some of the mercury and the likes, but that disappears as the sodium. You see the sodium lines now appearing, but they're also starting to broaden very quickly. And what you're actually wanting to look for is in the sodium lines is you see the dark space appearing, which you couldn't really see on the low pressure lamp at this resolution. But that dark space will appear and will broaden along with the rest of the lines. So we're actually getting an area of light being absorbed and expanding, as well as the expansion of the actual lines themselves as well. You can see it there starting to appear, the dark space is appearing. If we look kind of closer in at it, you can still see as the pressure builds up in that lamp, the dark space is extending. Now it extends to the point where it's wider than the original low pressure sodium light. This is a resonant absorption that's going on here.